Welcome to the fifth and final lecture of the course Statistical Problems and Simulation. In this lecture we will discuss hypothesis testing and statistical validation. I, who will be presenting this, is Jens Zander. I'm a professor in radio communication systems at the Department of Communication Systems at the School of ICT at KTH in Stockholm. Hypothesis testing is a concept we already discussed in Lecture 1. In simulation studies, we typically want to answer questions like, is the expectation of a random variable x found in a simulation larger than some other expectation of a random variable y? Or is a sample sequence outputted from a simulation x1, x2 to xn? Are these random variables drawn from the same distribution px? We may formulate this type of questions as hypothesis, and a hypothesis a statement. For instance, the hypothesis H0 is the statement that the expectation of x is larger than expectation of y, and we want to test the truth of this statement. Is the statement true? This is the concept of hypothesis testing. The second statement could then be formulated like this: if x is a discrete random variable, taking the values 1 to k. Since the output we get from our simulations are random variables, we can of course never perfectly ascertain whether a certain hypothesis is true or not. But the second best we can do is to expose the hypothesis to a statistical test. The concept is very similar to parameter estimation we discussed previously. For this purpose, we use a test statistic. A test statistic cap t is a function phi of a number of observations. Phi is a deterministic function. The x1 to xn, they are random variables, so t will be a random variable. And then we compare cap t to a threshold, or we determine if cap t is in a certain range of values. In this particular example, we compare cap t to threshold t, small t, and if cap t is larger than small t, we cannot reject the hypothesis, but if it's smaller than small t, we reject the hypothesis. The performance of such a test is measured in terms of something called a p-value. And the p-value is defined as the probability of false rejection. And this is the probability that we decide to reject the hypothesis, even though the hypothesis is actually true. So let us apply our hypothesis testing method to our first question. The question whether x1, x2, and xn, an observation we make of a discrete random variable, are they drawn from a given distribution px? We formulate a hypothesis h0, that is simply that the probability of x equal to I is pi. It's a simple definition of the distribution. And we construct our test statistic in the following way. We count the number of occurrences of outcome I, and we call that ni. So basically we put them in a vector, so we have a histogram of the number of occurrences of outcome I. And then we compare these outcomes with the expected value of the number of occurrences should occur according to the hypothesis of H0. So we form the square error between these two and normalize them. So we get the sum where we have the number of occurrences, and we compare this to NPI, which is the expected number of occurrences given the hypothesis H0 is true. And from statistics we know that such a sum is approximately chi-square distributed with k minus 1 degrees of freedom. We can clearly see that if the Ni is very close to the NPI. If the number of occurrences in our sample is very similar to the number of expected occurrences, then the sum will take a very small value, and the hypothesis is likely to be true. But if the discrepancy is big, then the squares will become large positive numbers, so t will take a large value. So if we compare this threshold with small t, then if t is larger than a certain threshold, then we will reject the hypothesis. And the p-value is of course the probability that we reject the hypothesis, even though hypothesis H0 is actually true. And looking at what a chi-square table looks like, it's you can see the distribution function. It looks like that. And for a very large number of degrees of freedom, of course, it will approach a normal distribution, since we have a sum of random variables. Now let's apply this in a simple example. The question here is, are the numbers listed here, 2, 1, 4, 6, numbers between 1 and 6, are they likely to be outcomes from an experiment where we roll a fair die? And the question that we have in front of us is to test our hypothesis, and the p-value should be less than 0.1. So how do we do that? Well, we start by forming our histogram, and Ni is the vector of the occurrences. So in this example, we have 24 occurrences total, and in this case, a 1 occurred 3 times, a 5 occurred 5 times, and so on. And of course, if it's a fair die, the hypothesis H0 is that all these outcomes occur with the same probability 1/6. And we construct our test statistics, and we compute it, and we get the value 2.5. And so now the question is this value above the threshold that corresponds to the p-value 0.1. So we have to go into our chi-square table. For 5 degrees of freedom, we have observe we have 5 different categories, so there are 5 variables we compare. And as we can see from our table, for 10% p-value, if we have 5 degrees of freedom, that gives a threshold value of 9.2. And 9.2 is much larger than cap t. So in this case, we cannot reject the hypothesis at the 0.1 p level. And this could also be seen since the values in the histogram are very close to the average value, which is 4. So in the previous case, we discussed the discrete random variable. How do we do it when we have a continuous random variable? Well, there are a couple of methods available. The obvious method is, of course, to discretize the continuous variable, and instead of having continuous range, we split the x-axis into bins of small sizes, and of course you can optimize the size of the bins. And you do the same way as in the discrete case. Then you count the number of occurrences of the random variable in the different bins, so you get a histogram, and then you do the chi-square test as in the previous example. There is, on the other hand, another method, and that is called the Kolmogorov-Smirnov test. And this test is based on the empirical distribution. And what you do is basically you compare the empirical distribution with the actual distribution according to the hypothesis H0. So FEX minus FEX. And then you take the maximum value over all x's. So where the difference between the empirical distribution and the actual distribution according to H0 is the largest, that will be our test statistic D. And you compare the statistic D with the threshold small d, and as you expect, if D is very large, discrepancy between the empirical distribution and the real distribution is very large, we are likely to reject the hypothesis. And the p-value is exactly the probability of doing this rejection, even though H0 is true. The interesting thing with this p-value is that it actually is independent of the distribution f. So we can numerically or by simulation determine this p-value. And we can use simplest possible random variable that could be the uniformly distributed variable. Here we see how a table of Kolmogorov test critical values D look like. In the vertical we have the number of observations n, and on the horizontal we have the p-value here called alpha, 0.1, 0.05 and so on up to 0.2. And that brings us to quiz 1. We have here an observation of 10 random variables. And the question is, are those random variables drawn from a uniform distribution, which would be our hypothesis H0? And we have the empirical distribution of those variables, and that's the blue curve in the diagram on the right-hand side. And we also plot the distribution of a uniform random variable, which is the straight red line in the curve. And your task is now to use the Kolmogorov-Smirnov test to check if the hypothesis can be rejected at the 10% p level. As usually, you should pause the recording at this point and try to solve the problem on a piece of paper. And when you're done, you can restart the video and we show the solution. And here is the solution. What we do is that we go into our graph and we find where the discrepancy between the empirical distribution, the blue curve and the red curve, is the largest. And we find that's somewhere around 0.7, and the difference there is 0.26. And what we do is that we take this number and go into the table in the previous slide of the Kolmogorov-Smirnov critical value distribution and determine whether this number 0.26 is larger than the small d value that corresponds to a 10% p-value. And looking in the table, we find this p-value to be 0.368, which is smaller than 0.26. So our discrepancy of 0.26 is not large enough to reject the hypothesis at the 10% level. So let's look at the other type of hypothesis testing techniques that we're going to study in this lecture. And this is usually called the two-sample problem. We have two samples, could be of different size. In this case, x1, x2 to xn, and we have another sample, yn, y1, y2 up to ym. And the question is, are they drawn from the same distribution? So the hypothesis we want to test is that H0 is that x, the vectors x and y, are independent and they have the common distribution. And how do we approach this? Well, we form a test statistic here called the rank sum. And this is how it's done, that we take the sample values x1 to xn and y1 to ym, and then we put them all in the same vector and we sort them according to size. So in this example, x1 and x2 are the smallest one, and then comes y1, and then so on until all the n plus m values have been sorted. And R1 is then called the rank of the value xi, so which place in the order from the left the value xy appears. And what we do is that we form a rank sum statistic, which is the for instance taking the smaller set. If let's in this example, if n is smaller than m, then it will be the rank sums of the x's. And the idea is, of course, if x and y have the same distribution, then they should be sort of evenly distributed in this sorted vector. So the rank sums of the x's and y's should be about the same. If the rank sum of the x's is very small, meaning that all the x's occur to the left in the vector, in the sorted vector, or reversely, if the rank sum of the x's is very, very high, corresponding to the case when the x's occur only to the right in the sorted vector, then we would reject the hypothesis. So if the rank sum is smaller than C1 or larger than C2, we would reject the hypothesis. The performance then is, of course, that we reject the hypothesis even though it's true. So if the rank sum falls outside these values C1 and C2, we will reject the hypothesis. Another way of seeing this is that we want to test whether both variables x and y have the same distributions, or overlapping distributions, or if they have if that is the discrepancy between the two distributions in the right-hand example. So let's do a simple example to illustrate the Wilkinson rank sum test. We have two temperature observation series, one with 7 observations, the x's, and one with 4 observations, the y's, marked in red here to simplify the recognition of the different values. And the question is, are they drawn from the same distribution? And as usually, we form our hypothesis H0. X and y are independent and have the same common distribution. And we start looking at our rank numbers. We form the vector z, which now contains all the 11 values, and we sort them in ascending order. So the lowest is to the left and the highest is to the right, and we can see the different rank numbers. So the first value of x has rank number 1, and the second is a y, there's a rank number 2, and so on. So the rank numbers of the x's are black here, and the rank numbers of the y's are red. And for sake of simplicity, we look at the rank sum of the population with the lowest number of values, and that will be the y's. So we look at the rank numbers of the y's, which are the red ones, 2, 3, 5, 6, and we compute the rank sum, which is 16. Now the question, is 16 large or small, or does it fall into the range where we should reject the hypothesis? Remember, if R is very small, then meaning that all the y's are gathered to the left in the vector z, or if R is very, very large, corresponding to the case when all the y's are collected at the right-hand side of the vector z. These two cases correspond to the situation where we should reject hypothesis h0. So what can R be here? What are the range of permissible R's? You can see here that R should lie in the range between 10 and 38. 10 corresponds to the case when all the y's are in the left-hand side of z. So if they occupy rank numbers 1, 2, 3, 4, that corresponds to R equal to 10. And conversely, if they're on the right-hand side corresponding to the rank sum numbers 8, 9, 10, 11, that would correspond to R equal to 38. So R is in this range. So should we reject the hypothesis or not? Well, we have a small table of the Wilkinson test statistics. In the textbook, there are some examples on how you can compute those values. We have, in this case, our numbers m equal to 4, n equal to 7. And we can see in the table here below that at the p-value of 0.115, the range is 17 to 31. So 16 would not fall into this range. And so at the p-value of 115, we should reject the hypothesis. But on the other hand, if we have a p-value of 0.82, the range is 16 to 32, and we cannot reject the hypothesis. And as you can see, as the p-value gets smaller, if we want to, this probability that we make erroneous rejection gets smaller and smaller, the range gets larger and larger. And you can see the limiting value is, of course, 10 to 38 at the upper portion of the table. So the conclusion is that the hypothesis can be rejected at 11.5%, but not at 8.2%. The p-values in the Wilkinson rank sum test is slightly difficult to compute. In the textbook, you will find a recursive method of computing the p-values for arbitrary m and n. However, if you have large sample sizes, when the sample sizes m and n are larger than 10, it's easy to see that the test statistics R is about Gaussian distributed, with mi k and sigma k, where the average mi k is corresponds to the case when both x and y are sort of evenly distributed, evenly spread over the vector z, and have the same rank sum. So let's wrap this lecture up with a final quiz. 4 statements. More than one answer can be correct. Pause the video and try to figure out the correct answers, and restart the video to get the correct answers. And here are the correct answers. The p-value is not the probability when we reject the hypothesis when it's actually false. It's the probability that we reject a hypothesis when it's actually true. B, it's correct. The Kolmogorov-Smirnov test statistics is independent of the distribution of the random variables we're observing. The mean square error sum in the discrete goodness of fit tests are not Gaussian distributed, they are chi-square distributed for a small number of categories. And the Wilkinson test does not require sample sizes to be equal for the 2 variables that we compare. So again, if you have missed any questions, it's a good idea to go back and review some of the previous parts of the lecture. And this concludes lecture 5.